As we start thinking about interp for our class-oriented curly, then we will need eventually to deal with send. And remember, send is a dynamic method call. So even though we can see in this example that the object created here is a pos in 3D, in principle there's a more complicated expression here that eventually delivers a pos in 3D as its result. So that when we call this mdis method, we're going to have to somehow look inside that object to find the right method. Before, we packaged all the methods up with the objects, but now we no longer need to do that. If we just say what class the object instantiates, pos in 3D in this case, then we'll be able to go look at the pos in 3D class declaration and find the methods there. Along similar lines, we don't need to keep the names of the fields with the objects. We don't need to duplicate that information. When we go look at the pos in 3D class, we will find out that it has x, y, and z fields, and so when we're using the fields, we can use the class to get the mapping from names to values. So what this means is we have a more minimal representation of objects, deferring all of the field names and method name information in the class that the object instantiates. So that means we're going to have our values are numVs and objVs, where the objV is a class name, just in our picture on the previous slide, and field values, which is a list of values. Now, we don't have to keep the symbols for the field names. The field names are in the class, which doesn't have any values because, of course, it's a class. It's not instantiated as an object. It doesn't even have initialization expressions because we're letting new deal with that. And a class has methods just like our objects did before. It's a mapping of symbols to expressions for the body of the method. So that means our interp is going to need to take the expression that we are currently interpreting. It'll start out as the main expression. But as it evaluates that expression, it'll need to find classes to look up field names and methods. So our interp, in addition to the expression, needs to take this list of class declarations. So you notice the class doesn't have the class's name itself. We're just going to pair it using a tuple, pair the symbol for the class name with the class, and then keep a list of those, and then we'll be able to use our find function to go find classes in that list. There's two more values here for interp, and those are the this and the argument, just like we had with objects. And of course, interp needs to return a value. So really what we've done here is add this list of classes into our interpreter, just like way back when we had a list of function definitions before we introduced lambda. Looking at a concrete example, suppose that our main expression, or the expression we have left to evaluate, is just a 10, a literal 10. Then we can have a list of empty classes. The whole program could just be 10. We will have to have some dummy object. So now we make an obj not with an empty list of fields, an empty list of methods, but with some name, the class that the dummy object claims to instantiate. So we'll just use object by convention for that. It's not a real class. We can't call any methods or use any fields on it because there is no definition of object. And then we have an empty list of field values since there are no fields. And the numv here is just the dummy argument. So again, interpreting the expression 10 will give us the number 10. To make more interesting examples, we're going to have to fill in some classes here. So let's take our running example, posin and posin 3D, and turn it into class records. So class C is the constructor for a class capital C. A posin has an x and a y field, so that's why we have list xy here. And it has mdist and addist methods, so that's why we've got this list. And we're going to combine that class C with its name posin as a tuple. And then posin 3D class is similar. We've got the name that we tuple with the class, and it has x, y, and z fields, and so on. And you see we have gets and sends inside. The gets are like we had with objects, and this send, this is a static send to the posin class. And then because we're going to run lots of examples with posin and posin 3D class, let's make us a helper interpreter that's an interp specifically to interp of a main program given these posin declarations. So interp posin will take an expression and call interp with a list of these two class declarations and the initial dummy object and the dummy argument. So now we can look at an example that instantiates a posin. So we're using interp posin. That means we're calling interp with those two class declarations. So when we do new e of quote posin, we will be able to create an object that's an instance of posin, and we'll be able to look up that posin as we need to in the classes to make sure there's the right number of fields here. So we have two field expressions, These expressions get evaluated to the numbers 2 and 7, so that's why we have number values 2 and 7 as the field values in our object. To make even larger examples, let's take this expression and give it a name, new posin27. So whenever we use new posin27, that's just shorthand for this expression that generates a posin that has 2 and 7. And if we interp the larger expression send on that new object, the mdis method, then we expect interp to work as follows. The new posin here is going to evaluate to that obj v, and then send will need to find the posin tag on that object and look for the mdis method in the posin class. So it'll look in our list of class declarations, which includes posin class. It'll find the one that is attached to the name posin, because that's the tag that's associated with the object result of new posin7, and it'll find mdist, and so that's how it will end up calling this plus expression here. This new posin7, 27 makes an object with 2 and 7, so when we get the x field it'll be 2, when we get the y field it'll be 7, we'll add it up, and that's how we get a 9 at the end here. This num-e goes in as the arg value. The value 0 goes in as arg, but we don't use arg inside of mdist. If we look at sending new posin 531, an add dist method with new posin 27, new posin 531 is going to be a shorthand for creating a posin 3D with field values 531. So we will look for add dist in a posin 3D. So when we find this posin 3D in the list of classes, we'll look for add dist here, and it will say do a static send to posin's add dist, passing along the same argument, so the posin with 2 and 7, and sending it to this. So that means that we'll find posin this time instead of posin 3D, and find the add dist method in it, which will be right here. And this argument is being passed along as rd, and send e will make sure that this is still the same this, so it's still the posin 3D object. And so on. When we do this dynamic dispatch to mdist on a posin 3D object, we will do this addition. That will give us a 1 to add to the result of 5 plus 3, so we'll get a 9 here. And then when we send the mdis method to the argument, that remember was this posin 27, we'll also get a 9, add those together, and that's why we get 18.